So when we start with this bit of review, we're going back a ways in time, I guess, because it's probably been a couple of weeks since we talked about things like this. But as far as your techniques go, hopefully it's not so far back that you can't really remember what we're talking about. If you got into this situation, and that just does not display quite right. Let me just see if I can adjust the zoom. If you got into this situation, the first thing, of course, that you want to try to do is go with the easiest technique first. So is there a way to make this easy? Sorry? Yeah, split it up into 3 pieces. So that was just a reminder that in some questions, if you kind of think it a little bit at first, you'll be able to make it easier as we move along. So if I was to find this integral, it's actually pretty easy. I can just use the power rule on all of these. Minus 2x and minus 1 over x plus a constant. Okay? So the next question that I wanted us to look at is, I'm throwing it in there. It's something we're familiar with, but maybe we should take a look at because I'll show you what the AP exam would typically do here. So I'll just read it to you while you're copying it down. Estimate the area below the curve, y equals a quarter x cubed, from 0 to 2, using 4 rectangles and a left point rule. Is your approximation larger or smaller than the real value? So let's, just to make
what 4 points?
Well, that's what we're going to discuss here, okay? We're going to draw a picture. There's a lot of information there, so before we try to make sense of it, we should try to get some of it down into a picture. So maybe I'll give you just a minute in case you're copying it down. So if we put this into a picture, I'll start it on a different slide. So roughly our picture would look something like this for the part that we're concerned about. This would be from 0 to 2. It would look something, oops, sorry, that's obviously supposed to be a 2. And then that's supposed to be the 0 there. And it says it's going to use 4 rectangles. So how wide will each rectangle be? A half, right? So let's mark down those spots. So here's the spots where the rectangles would be. And a left point rule means when you look at the rectangle you're given, you're going to pick the left side. Okay? So the left hand would look like this. There would be no height in that rectangle. When I look at the next piece, it's going to be the left side that I use. And again, I'll use the left side and the left side in order to do my rectangles. And I'll just write this up here. It's y equals 1 quarter x cubed. So the points that I'm looking at, right, I should be able to get an area estimate with those rectangles. Now just sometimes it's simple, like, you know, x squared or something you'd be able to calculate easy. Quite often they give you a table of values, so you don't have to do the calculation with the calculator. So quite often they would just give you a set of values and you'd have to pick the correct ones from the table. So in that sense, you know, it's a little nicer that you don't have to calculate anything. But if we look for the area, of course there's no area in this rectangle. And that was awful, let's try that again. In this next rectangle, it's a half wide, and the height, well, this is 1 quarter a half cubed, so that's going to be 1 out of 32. Okay, so half times 1 out of 32, this is going to be 1 out of 64 for its area. Okay, so the next piece that we're up is here. It's going to be 1 quarter 1 cubed. So the area is going to be 1/2 times a quarter. So I end up with 1/8. Okay, and then in the last triangle, last rectangle, this is going to be 1 quarter And at 1.5, it'd be easier to look at it like 3/2 cubed. So this would be 1/4 times 27 out of 8. This is just having a bad pen day here. 27 out of 8. Okay, so it would be 27 out of 32. So my area I could get is like this. It would be 27 out of 64. So we can add those pieces up to come up with an estimate, and I believe we get an area which is about 0.5625. So let's see here. It's going to be, oops, did I add that wrong? I may have added it wrong. Let me just double check. Get the calculator out. So 1/64 plus 1/8 plus, no, that's correct, 0.5625. Okay, so we can find that calculation, but quite often what the AP exam will ask you to do is try and extend your thinking a little bit more. It'll say, well, is this greater or less than? And the picture makes it obvious, so what do you think? Is this bigger or smaller than the actual area? Okay, so the reason it's smaller, you can see it in the picture. The reason it's smaller is there's that missing gap of area, but what if we didn't have the picture? What if we didn't have the function? What if the only clue that I gave you was this? Okay. That's true for the function you're looking at right now. How do I know that the first derivative is greater than 0? Yeah? Well, we could just take the derivative, but why? How do I know that it's... look at the picture. How do I know it's greater than 0? Well, you could look at the slopes, that's true. But there's an even easier way, right? What's a derivative again? You have two possibilities. What's a derivative? A rate of change. We just talked about slope. So if it's a rate of change, how do I know just by looking at the picture that the derivative is greater than 0? It's increasing, right. So it's increasing, so the first derivative is greater than 0. Now why would then a left point rule have an area which is smaller than the true value? Why is that the case? Because ultimately what I'm going to ask you is something like, well, what happens in this situation? Let's flip some things around. Let's make it less than 0 and use a right point rule. That's the only information I'm going to give you. Will the area be bigger or smaller? So for those of you who are looking at this, tell us why is the area, if that's the only clues you've been given, how do you know? Ming?
Because it's increasing, the left point is smaller than the right point.
Yeah, if it's increasing, the left point is always the smallest, right? So for example, if I'm looking at this area here, as I increase, the left side is always the smallest of those values. Therefore, the rectangles I draw have to always be less than or equal to the curve. So that's how I know the area is underneath it. Okay? There's nothing wrong with doing a quick sketch like a picture. For example, what do you know about the graph if this was what I said? What do you know about it? Sorry? It's a decreasing graph, and I'm using the right point rule. So let's just see here. There's one type of decreasing graph. There's another. So could we say anything about, is there enough information there? If we tried to draw some right side rules in, like for example, had those pieces, or it could be like that. Why is it this time that it's smaller than the area? how is it that this time it makes the, using a right point rule and a first derivative that's negative, how is it that you know the area must be smaller? Right? So the function must be decreasing. And if we use the right point, what does that mean? All right, well, it looks like we're going to have to practice this one a little bit more. You're right about the decreasing, but if I use the right point, this is the right point of the rectangle. The right point. The right point. So why is that now that I know it's got to be less than the area?
It has to be less than the
Yeah, well, the right is going to be the smallest because it's decreasing. The further to the right I go, the smaller the value is going to be. So we're going to explore those ideas a little more. They may even go as far to say, compare the left side to the right side to the trapezoid rule. So can we figure out what would happen? Let's just take a look at this picture number 1, and let's see if we can think like an AP exam. If we had the L for left-hand rule, the T for the trapezoid, and the R for the right-hand rule, can we order these? Like maybe it's like that. Can you tell me maybe one of those? Like, can you say, oh, the trapezoid has to be bigger than the left side rule? Can anybody come up with one of those? Based on picture number 1?
The
Right
right hand is less than the trapezoid.
hand is less than the trapezoid rule. Okay, yeah, I would agree. Oh, sorry, hang on a second. Oh, no, yeah, that's right. Wasn't sure if I wrote it down wrong. Okay, what else?
The left hand is bigger than the trapezoid.
Left hand is bigger than the trapezoid rule?
Yes.
Okay, so it looks like you got a trapezoid sandwich there. So you could probably write this as right less than trapezoid less than left. And yeah, that would in fact be, if this was the question, it probably would have said A, left trapezoid right, B, right trapezoid, and it would just jumble them around, and this would be the multiple choice to be looking for. So anyways, as I said, you have a lot of that AP knowledge. It's just that we got to kind of work our brains around how it is that these style of questions is answered. So we'll practice those more, but I wanted to throw one in for now because this is a fairly short review. With fundamental theorem of calculus, you should be able to evaluate these. It's the same as doing your antiderivatives, only now you're evaluating it at these points. If it's hard to read, the bounds here are -2 to 2. So this would simply be a power rule, x to the 5th over 5 plus 2x cubed over 3 minus 5x from -2 to 2. And the way you evaluate it again is you're going to be looking at the antiderivative of 2. Take away the antiderivative of -2. Okay, and if we put this in a calculator, I believe you have those two values, which, let's see here, puts us at let's say 3.46. The other one I'm bringing up here is because it's tempting to use the power rule. It looks deceptively simple, but you need to remind yourself that one of the other things we deal with is natural log. So how is it that you know this is not a power rule question and that it involves the natural log? The exponent is -1. That's right. So if the exponent's -1, we can't end up doing this, right? This does not make sense. So that's how we know we have to end up going to natural log. So this is going to be 3 times the natural log of x, evaluated from 1 to 6. So this will be 3 natural log 6 minus 3 natural log 1. That one I can simplify. So I would just end up with 3 natural log of 6. Okay. So the last thing in this first half of review is we'll just see if we can recognize which techniques are most appropriate. So here's a few questions. Let's take a look and see if we could come up with a solution to working with one of them. So if you look at the first example, what technique do you think you might want to work with here? Yeah, substitution sounds like a good call to me. If I look at this, I see an x cubed. So this could potentially be my function, which means this one here could potentially be my derivative. So this would be a good one to work with for substitution. So let's make my substitution here. If u was equal to x cubed plus 3, du would be 3x squared dx. So that means I would want to put a 3 in front. So I would need a 1/3 to balance it out. That looks like a 2. I don't know why this pen is giving me such problems today, but I swear I'm not writing that messy. I don't know if that was any better. But anyways, so if I make my substitution now, I'll have 1/3 the integral of root u du. And that's a lot easier to work with. So this will become 1/3 u to the 3/2 divided by 3/2, or 2 u to the 3/2 divided by 9. And our substitution was for x cubed plus 3. So I'll fill that in and add my constant. So I'm going to let you try doing the next 3 and see if you can come up with a good strategy or a good technique to integrate the next 3. Just jog your memory. There are a few of them out there. What one would be most appropriate here? Okay, so let's see here. If I use the power rule, that means I'm going to go to 1/2, and that'll be a -1, so it'll go u to the -1 over -1. So I could rewrite this as -1 over 2u plus my constant. And that'll be, let's see here, we made a substitution. So -1 over 2x squared plus 6x minus 5 plus a constant. Okay. So the next one there, this cos x root sine x. When you're deciding what to substitute for, I mean, it could go either way since one is the derivative and function. They're fairly closely related. But it would be nicer to get rid of the square root. That's kind of the difficult part of it. So let's try and target that, because the square root would be nice to get rid of. So that means my differential would be cos x dx. And lucky for me, that is actually ready to go. So this will be du over root u. And if I use the power rule backwards, that's going to be u to the 1/2 over 1/2. So that'll be 2 root u, or 2 root sine x plus a constant. Yeah. Say it again a little louder. Sine's derivative should be cos x, right?
Yeah.
You got them. Cos x would be negative sine, so there would be a negative in there if it was, if we made the if we substituted the other way, there would have been a negative. So in the next one here, I would suggest when you're looking at it and you don't quite see where to go, sometimes it's helpful to split it into pieces so that you can look at each piece more clearly. So if you do this, when you rewrite it, it might jump out a little more at you what your substitution is going to be. This function here, very close, the derivative is very close to this function here. So since I can see that relationship, it gives me a place to start. I'm going to make my substitution 1 over x. So du will be negative 1 over x squared dx. So I can see I'm missing that negative. So let's put the negative back in. So I need a negative for both to balance it out. So I'll now have the integral of, the negative integral of e to the u du. And that's everybody's favorite because it has the best derivative and the best antiderivative. So that means I just need to make my replacement for u, which was 1 over x. So that's about the extent that we're going to jog your memory today. We'll carry on in the second half next day.